This is the fifth topic in the probability and stochastic processes course, in which you're going to talk about expectation. Expectation or expected value is a number that expresses many things about the behavior of random variables. It mainly expresses the average nature, the average behavior of a random variable. If R is a random variable defined on a certain sample space S, then the expectation or the expected value of that random variable R is defined by the sum of all omega inside of S, R omega multiplied by the probability of the omega. So the value of the random variable for that particular outcome multiplied by the probability of the outcome. Well, this is why we call this also average, because the value of that outcome, the value that corresponds to the outcome in the random variable, is weighed by its probability. Suppose S, the sample space, is the set of all students in this class, and we select a student randomly and uniformly. Let R represent the grade of the selected student. Then the expectation ER is the average grade of the class, namely the grade of that particular student, the grade of every student multiplied by the probability of that student. So if the probability of the student are just the same, so we are simply taking the average grade of the class. Let's take another example. Let R be a random variable that represents the value produced by tossing an unbiased die. So there are 6 possible values, namely 1 until 6. And because it is unbiased, that means the probability of each one of them is occurring is equal, namely 1/6. Then the expectation of R is 1 multiplied by 1/6, namely the possible value multiplied by its probability plus 2 multiplied by 1/6. So you see all the value weighed by its probability, and the final result is 7 divided by 2. And we call it the expected value. And the name expected value is a bit misleading actually. We do not actually expect that the die will produce 3.5. It cannot produce 3.5. It can only produce 3 or 4 or 5 and so forth. When we are interpreting a probability or expectation, then we have to use a large number interpretation. In this case, this simply means that if I'm doing the experiment, for example, 1,000 times, then the expected value will be the value of the whole, the summation of the whole possibility, the whole tossing will be around 3,500. Or if you take the average, then the result will be 3.5. Expectation is different from median or middle value of a distribution. The median of a random variable R is the value X element of the range R such that the probability of R is less or equal to X is less or equal to 1/2, and the probability of the rest, namely R more than X, is also less than 1/2. So this simply means that the value in the range of R in which the left side has the probability 1/2 and the right also has this probability 1/2. The expectation of uniform random variable. In general, if Rn is a random variable with a uniform distribution with sample space, the set of number from 1 until n, then the expectation of this random variable is equal to the sum of I is equal to 1 until n, I, namely the value of the random variable multiplied by 1n. the probability, which is equal to n plus 1 divided by 2. So simply the average. The expectation of indicator random variables. The expectation of an indicator random variable for an event is simply equal to the probability of the event. If IA is an indicator random variable that corresponds to event A, then the expectation of IA is simply equal to the probability of event A. We have an alternative definition for expectation. This definition basically connects the expectation to the probability density function of the random variable. If R is a random variable defined on a sample space S, then the expectation of R is equal to the summation for all x inside of the range R, x multiplied by the probability that the random variable L, R is equal to x, and this simply the same as the sum of all x inside of the range R, x multiplied by the PDF of x. And we have a corollary. If the range of the random variable R is the natural numbers, and we're starting from 1, 2, 3, and so forth, then the expectation of R is equal to the summation from I is equal to 1 until infinity, I multiplied by the probability of R is equal to I, and this is the most important part. This is the same, and this will make it easy for us later on. This is the same as this is equal to the summation from I is equal to 0 until infinity. The probability of x is larger. Yeah, the probability of x is larger than I. We will use this for mean time to failure. Mean time to failure is an important parameter in many systems design. Suppose a computer program crashes at the end of the hour with probability p. This simply means that the time is discretized to an hour, and we assume that an event, for example in this case the program crash, the crashing of the program, occurs always at the end of the time interval. So we are doing discretization. Now the problem is, what is the expectation of the time until the program crashes? How many hours do we have to wait until the program crashes? This expectation is called MTTF, the mean time to failure. How do we answer this? Assume C is a random variable representing the number of hours until the crash. Then what we are looking for is the expectation of C. C is a random variable with range, then the set of the natural number. Look at this. So the number of hours can be 1, 2, 3, 4, 5, and so on. Then based on the previous corollary, the expectation of C is equal to the sum from I is equal to 0 until infinity, the probability that C has value larger than I. And then how do we get this probability? Probability that C is larger than I. This is actually quite easy to determine. A crash happens after the ith hour, namely C is larger than I, even only if the program has not crashed during the first I hours. And this happens with the probability, well, the probability that the first hour it does not crash is 1 minus p. In the second hour also 1 minus p, and so forth. And because we have I hours, then this is equal to 1 minus p to the power of I. Therefore, the expectation of C is equal to the sum of I is equal to 0 until infinity. This part here is equal to 1 minus p to the power of I. Yeah, is equal to 1 minus pi to the power of I. And this is simply a geometric sum, an infinite geometric sum. This is equal to 1 divided by pi. In general, If a system fails every time step with probability p, then the number of expected steps until and including the first failure is 1 divided by p. And this is important for us. We are going to use this later on. It's called the mean time to failure. Conditional expectation. Similar to probabilities of events, expectation can also be conditioned on certain events. A conditional expectation of R given A or if A of a random variable R conditioned on event A is defined by the expectation of R given A is equal to the sum of all x element of range R, x multiplied by the probability of random variable R has value equal to x given A. So this simply means that take every possible value of the random variable, then multiply this possible value by the conditional probability of this value occurs. For instance, we can calculate the expectation of tossing an unbiased die with the condition that the tossing produces a value at least 4. Let R be the random variable for this tossing of the die. Then what we are going to look is the expectation of R if R has value more or equal to 4. Therefore, this is equal to the sum of I is equal to 1 until 6. There are 6 possible values of I multiplied by the probability that R is equal to I if R has value more or equal to 4. When do we have this? Well, the value can be 1, 2, 3, 4, 5, 6, and so forth. But then look at this. The probability that R is equal to 1, given that R is more or equal to 4, is of course 0. Because the condition is already more or equal to 4. So it is not satisfied. So for these 3 values, the probability will be 0. What about for R is equal to 4? Well, this condition is already satisfied. Then the probability will be, of course, 1/3. The final result, the expectation is equal to 5. The law of total expectation. Another use of conditional expectation is we can divide a complex expectation calculation into simpler cases. Let R be a random variable on a sample space S, and let A1, A2, and so forth be a partition on S. Then the expectation of the random variable is just the same as the sum for all I expectation of random variable R if AI multiplied by the probability of AI. So this simply means multiply the probability of the random variable condition on a particular event or a block, a partition or a block in the partition of S multiplied by the probability of that block. So that's why we call this the law of total expectation. We just sum them all up. Expectation of functions. Expectation can also be defined for functions of random variables. Let R be a random variable, namely a function from S to V, and we have a function right now, and this function is from V to the real number, and this is a total function on the range of R. Then the expectation of the function of this random variable simply the same as the sum of all omega, the function of R omega multiplied by the probability of the omega. So this simply means that take the function of the random variable multiplied by the probability of the outcome. And this is equivalent to say that the expectation of the function of a random variable is equal to the function of x for all x element of the range of R, the sum of all of them multiplied by the probability that the random variable has value x. An example, let R be a random variable for the value obtained from tossing an unbiased die. Then the expectation of 1 divided by R, for example, is a function of a random variable R. And this is given by this 1 divided by 1, this is according to the function, multiplied by the probability, plus 1 divided by 2, this is the function of the random variable, multiplied by 1/6, and so forth. And the final result is equal to 49 divided by 120. Expectation and gambling. Many interesting things can be explained with gambling, and we are going to use this often later on. And the simpler one is that it is what we call expected return. Suppose you win $A with probability P and lose $B with probability 1 minus P. Then the expected return, look at this, there are only two possibilities right now, winning or losing. So if you think about this in terms of the random variables, then the range of the random variable can only two, yeah, namely winning or losing. Wins happens with probability P, losing happens with probability 1 minus P, and if you win, you have these return what we call $A, and if you lose, we have this lose with $B. So the expected return is equal to P multiplied by A minus 1 minus P multiplied by B. For instance, if you toss a fair coin and win $1 for head and lose $1 for tail, then your expected return will be 1/2 multiplied by 1. So this is the probability. This is the first one here, the probability of getting head, and this one is the probability of getting tail, and this is the win, and win is the loss, yeah, and the final result is 0. In this case, it is called fair. So if the expected return of a game is 0, we call this a fair game. Expectation of sum. Expectation obeys a simple yet useful and powerful rule, linearity. For any two random variables R1 and R2, the expectation of R1 plus R2 is equal to the expectation of R1 plus the expectation of R2. Pay attention that there is no additional condition for this. So this applies for any random variables R1 and R2. And this can be easily generalized for any random variables R1 and R2 and constants A1 and A2, element of real number. Then the expectation of A1 R1 plus A2 R2 is equal to A1 multiplied by the expectation of R1 plus A2 multiplied by the expectation of R2. Look at that. So we simply take out the constants from inside of the expectation. For the case of more than two variables, we have for any, look at this, for any random variables. So this is just a generalization of the previous result. For any random variables R1 until Rk and constants A1 until Ak, then the expectation of the sum is equal to the sum of the expectation. The expectation of the sum of I is equal to 1 until Kai Ri is equal to the sum from I is equal to 1 until Kai expectation of Ri. What makes the linearity of expectation important is because it has no condition, and we need no assumption on independence. We don't really care whether those random variables are independent or not. Independence is something really difficult to prove or to assume, and maybe dangerous to assume. And this is important also if we use this to compute the sum of indicator random variables. The linearity of expectation is especially useful when we are dealing with the sum of indicator random variables. Suppose that during the dinner, n guests check in their hats. Those hats are mixed, and when the guests are about to leave, each receives a hat at random. Therefore, each receives his own hat with probability 1 divided by n. Why is that? Because there are n hats in the pool and we simply take one of them at random. So the probability that we select the correct hat is equal to 1 divided by n. What is the expectation of the number of guests who receive their own hats? This simply looks hopeless. Let's take a look at this. Let G be the random variable for the number of guests who receive their own hats. Hence, what we are trying to compute is the expectation of G. The only thing we know is simple. The only thing we know is that the probability of each receive his own hat is 1 divided by n, and this seems like a very simple trivial knowledge. But actually we can solve this easily by using the linearity of expectation. The trick is to express G as the sum of indicator random variables. Let Gi be the indicator random variable for the event that the ith guest gets his own hat. So this simply means, for example, G2 here has value either 0 or 1. It has a value 0 if the second guest number 2, doesn't receive his own hat, and 1 if he receives his own hats. So that means that if we sum them all together, this simply means we are summing those people who receives their own hats. Yeah, those people who do not receive their own hats will have value 0 for this one. Yeah, for this indicator random variable. It is clear that these indicator random variables are not independent. They are not independent. Yeah, they are not independent. If I don't receive my own hat, somebody else must not receive their own hat. But this is not a problem if you are dealing with expectation. Since Gi is an indicator random variable, then from previous lemma, we have the expectation of Gi is equal to the probability that Gi is equal to 1, which is equal to 1n. And by using the linearity of expectation of G is equal to the expectation of G1 until Gn. This is equal to the expectation of G1 plus the expectation of G2 and so on until Gn. And this is equal to 1n n times, which is equal to 1. And we can generalize this. In general, we have a good method to calculate the expectation of the number of events that are going to happen. Given any n events a1, a2 until an, which is a subset of the sample space, then the expected number of events that are going to happen is given by the sum of all the probability of those events. And we do not care at all about the independence of those events. Expectation of binomial distribution. Suppose we have a bias coin with probability of hat is with we have a bias coin whose probability of hat is p. Independently, the coin is tossed n times. What is the expected number of obtaining hat? Let G be the random variable for the number of hats occurring in the n tossings. Then, of course, like we have seen in the previous week, J has a binomial distribution, and the probability that J is equal to K is equal to n select K multiplied by p to the power of K multiplied by 1 minus p to the power of n minus K. So this is simply the binomial distribution, the PDF of the binomial distribution. Then the expectation of this random variable is simply the sum of the value of this random variable multiplied by the probability that the random variable has this particular value. But then after we have this it looks really daunting and difficult to simplify. How do we proceed? Well, we can try actually another way. We try to use the linearity of expectation for indicator random variables. But how do we express J as a sum of indicator random variables? Let Ji be an indicator, the indicator random variable for the ith tossing, namely only two possible values for Ji, 1 if the tossing produces head, 0 if the tossing produces tail. Therefore, look at this, J is simply the sum of Ji until Jn. So if a particular J here, if a particular J, let's say for example J2 does not produce head, then its value simply becomes 0. So it does not count. Therefore, the expectation of J is easy right now, is equal to the sum of I is equal to 1 until n. The probability of Ji is equal to n multiplied by P. And what we have been doing is we have just shown that this complicated formula here actually reduces to n multiplied by P. Yeah? So if we toss n mutually independent coins, we indeed expect to have n multiplied by P head. And look back again. Pay attention that we don't make any assumption about independence. What if the coins we use are not mutually independent? No problem. Yeah, of course they are not. Well, they may be mutually independent, but even though they are not mutually independent, from the linearity of expectation does not make any assumption on independence at all. Infinite sums. Now, the linearity of expectation also applies to infinitely many random variables. Let R0, R1, and so forth be random variables, but we have a condition, namely that their sum, the sum of all of their expectation, the sum from I is equal to 0 until infinity, the expectation of the absolute value of Ri is convergent, namely it has a definite value which is less than infinity, then the expectation of the sum is also equal to the sum of the expectation. The expectation of I is equal to 0 until infinity, Ri is equal to the sum of all of I is equal to 0 until infinity, the expectation of Ri. The expectation of product. If the expectation of sums is equal to the sum of expectations, similar thing does not always apply to product. Look at this. However, there are special cases where it applies, namely when the random variables involved are independent. So, for product, we need independent assumption. We need condition. It is conditioned on the independence of those random variables. For any two independent random variables R1 and R2, the expectation of their product is equal to the product of their expectation. And we can generalize this for many random variables, but then the conditions becomes more stringent. If random variables R1, R2, and on so forth until Rk are mutually independent, so we require them to be mutually independent right now, not just pairwise independent and so forth. All of them must be mutually independent. Then the expectation of their product is equal to the product of their expectation. Expectation of division. If S and T are random variables, then based on the linearity of expectation, we know that the expectation of the sum is equal to the sum of the expectation. Similarly, if S and T are independent, we have seen that the expectation of S multiplied by T is equal to the expectation of S multiplied by the expectation of T. How about division? Thus, expectation of S divided by T is equal to the expectation of S divided by the expectation of T. Well, the answer is not in general. Therefore, expectation of S divided by T is not equal to the expectation of S divided by the expectation of T. And the most important thing to remember for you is that the expectation of 1 divided by T is not equal to 1 divided by the expectation of T. We will see later on that these simple facts, are often forgotten when we are analyzing some system. So this is the end of the 5th topic in the course of probability and stochastic processes. Thank you.